Okay, we are going to be doing number 52 out of the textbook, and also one of the homework problems, one of the questions from the test. So number 52 has a diagram with a couple blocks. You have table, block with a pulley, wall. Now there's a string attached to the wall, looped around the pulley. There's another pulley hanging on the edge of the table, attached to a hanging block. Now, so the information we have, we're going to call the one on the table block A, the one hanging down is block B. Mass of block A is 2 kilograms, and block B is 1 kilogram. Now the question is, what's going to be the acceleration of block A? So it mentions to analyze the acceleration constraint, and I'm going to be doing a demonstration for this in class to help you understand it. But the idea is that for however far B drops, A is going to be dropping, or is going to be moving half that distance. So the way that works is going to be the acceleration of A is going to be equal to half that of the acceleration of B. It moves half the distance in the same amount of time, so whether it's a constant speed or an acceleration, it makes no difference. It's still going to be half. So what we're going to start with is a free body diagram for each individual block. We have block A, block B. We're just going to assume them to be point masses for the time being. So block A, you have force of gravity and the normal force, that's easy. And then you have two separate tensions acting on the block. For block B, again, just a point mass, you have the force of gravity acting down and the tension acting up. Now, just as a side note, Newton's third law says for every action force there's an equal and opposite reaction force. I'm just going to label the action-reaction forces, and that's going to be either one of these two, and those are the action-reaction forces. That's not going to affect the way we solve this problem, though. I just wanted to make sure you had that in mind. So, back to the problem. Newton's second law, F equals ma. F equals ma can be applied to either the entire problem, or it can be applied to small parts of the problem. So for the time being, I'm just going to apply it to each individual block. So the force on A is going to be equal to the mass of A times the acceleration of A. The force acting on B is going to be equal to the mass of B times the acceleration of B. Now, they may or may not be equal. I'm just clearly identifying them so you know which one is which and we don't get lost in the problem. So we have force on A, the sum of all the forces on A. Well, the normal force and the force of gravity cancel out. There's no friction, so we don't have to worry about that. So we only have 2T is equal to the mass of A times the acceleration of A. That's easy. Sum of all the forces on B, we have the force of gravity on B minus the tension is equal to the mass of B times the acceleration of B. Now, to keep going with this, we're going to be doing some substitution. We're trying to find out the acceleration, so we're trying to get rid of all the unknowns, all the values that we don't know, don't understand, don't need. So, since we have tension here and tension here, we can do some substitution. We can do it either way. We can substitute B into A or A into B. It really doesn't make a difference. It's just going to be a little bit of a different setup in terms of the algebra. I'm going to substitute A into B. So first thing I'm going to do is I'm going to solve this just for T. So I divide both sides by 2. So we're going to end up with tension is equal to the mass of A times the acceleration of A over 2. I'm going to substitute that into there. Let me give myself some more room to work. Now, this is going to be an exhaustive description just to make sure everybody understands it. You don't have to write out every single detail. This just helps you understand specifically what I'm doing. So we have substituted into here. So we have the force of gravity on B minus mass of A times the acceleration of A over 2 is equal to the mass of B times the acceleration of B. The only other substitution we're going to need to do is all the way back over here, and that is substituting the acceleration of A and the acceleration of B. Again, you can solve it however you want to. We can solve A into B or B into A. It makes no difference. I'm actually going to leave this equation the way it is, and I'm going to plug this into there. So I'm going to write it out ad nauseum for the time being. So we have force of gravity on B minus mass of A times 1/2 the acceleration of B over 2. Is equal to mass of B times the acceleration of B. So let's keep going with this. Actually, I think what I'm going to do is I'm going to start plugging in some of the numbers to make things easier to cancel out. So we have force of gravity on B, so we have the mass of B, which is just 1, times the gravity, which is just G, so that's just G, minus mass of A is 2 times 1/2 acceleration of B over 2 is equal to the mass of B, which again is just 1, is equal to the acceleration of B. So 2 and 1/2 cancels, so we end up with just G minus AB over 2 is equal to AB. The rest is just some simple algebra. I'm going to multiply everything by 2, so 2G minus AB is equal to 2AB. Add AB to both sides, and you're going to end up with 2G is equal to 3AB. So the acceleration of B is equal to 2G over 3. Multiply that out. Gravity is 9.8 meters per second squared times 2 divided by 3. You're going to end up with the acceleration being somewhere around 6.6. But we're actually looking for the acceleration of A. So if you finish that off, the acceleration of A going all the way back to here is half that of B. So the acceleration of A is going to be 3.3 meters per second squared. And I think that's going to cover it.